Hello, thank you for being here today. We're First Tech Challenge Team 6448, the Jesuit Blue Jays, and we would like to take a moment to share with you all about our robot game and our robot itself. During the autonomous period, the robot can sense the number of rings on the field, in this case 0, then drive up to the goal line and shoot into any of the 3 goals or to one of the 3 power shots. Our robot shoots 3 rings into the top goal. It then delivers the wobble goal into the correct zone marked off with the squares of tape, depending on the number of rings sensed at the beginning of the match, and then it navigates back to the white scoring line to end off its autonomous period. Next is the driver-controlled period, commonly referred to as teleop. During this period, 2 drivers can control the robot with the controllers that they just picked up to continue to score rings in the low, mid, or top goal. The higher the goal, the more points they score. In this run, we were able to score 11 rings into the top goal. Now that you understand a tiny bit more about what the robot is doing in the background, let's backtrack a bit to understand what the robot game this year actually is. Just like in years past with FTC robotics games, each game consists of a 30-second autonomous period in which the robot has to be completely controlled autonomously using its own sensors and programs without any driver input to accomplish its tasks. Then there is a 2-minute driver-controlled period where up to 2 drivers can control the robot and try to score as many points as possible during the time. It typically has a simpler goal in mind during this period. For instance, this year, instead of having to deal with all the wobble goals, you only had to focus on shooting the rings into the 3-tiered goal. The last 30 seconds of the driver-controlled period is called endgame, in which a number of other scoring possibilities open up. For instance, this year, we can now once again hit down the power shot targets, and we can also deliver the wobble goal outside of the playing field for extra points. Now let us head over to the rest of the team to get a full description of how our robot works to accomplish all of the challenges posed to us with this FTC game ultimate goal.
To start off, this little latch right here is the beginning of sort of the whole process. This latch releases the intake, which pulls the rings in. The point of this, being a whole latch, is it takes all of the torque of holding this big piece in place off of the servo. It actually is inspired by deadbolts, and it pulls all of the force is being put onto this metal bar. All the servo has to do is move this little piece and the whole thing opens up.
So now after the intake opens up, you can see that it's a very simple mechanism that's composed of just this rev hex motor and this custom printed intake star. So we activate the hex motor and we can feed a ring into our intake right here. And so you can see that the Ninja Flex is very grippy, allows it to grab onto the ring very easily, and it feeds it into our ramp, which is made of a 3D printed box and an acrylic plate for the ring to slide on. So then our conveyor belt, which is also driven by another hex motor, has these 3D printed heads that grab into the middle of the ring so that after the ring's taken in by the star, it transfers to the conveyor belt to bring it the full length up of the intake and into our hopper.
And now here you can see we have a hopper set up that is designed to act as a buffer between the intake and the launcher itself. So this allows us to preload rings for the autonomous period, in which we fire 3 rings quickly into the goal. And it also allows us to hold 3 rings so we don't have to constantly maneuver to pick more up. And it also has our firing mechanism, which is a servo right here that uses this little arm to push rings into the launcher. And it doesn't work for more than one at once, but that isn't usually a problem because the launcher is pulled up.
From the hopper, the rings come into the launcher, and the motor, which is spinning the wheel, grabs the ring and fires it in the front.
For this year's competition, one of the goals was to deliver this wobble goal into one of the zones over here. So for that, we used a 3D part to help mount a 90-degree rev motor, which helps spin this bar, which this piece then can grab the wobble goal lifter, and then it brings it back up, and then it can drop it. For the part, we've also have this backbone right here, where to help support this long piece, so the entire weight of it isn't on this one thin bar, so it's not bending and warping it.
One of the main mechanisms on our robot this year is this set of wheels. These three spring-loaded wheel housings here are used for our odometry system. The odometry system just allows us to use encoders on these wheels to track how much the wheels rotate, how many times the wheels rotate in either ticks or rotations. We use these odometry wheels in conjunction with our global coordinate system. The global coordinate system takes every part of the field and maps back to a specific origin point, allowing us during our autonomous phase to not only know the position of the robot, but also the shooting line, the wobble goal landing zones, and the goal itself. We can also use it during a actual teleout phase to aim our bot towards the goal whenever we need to.
So a lot of the code this year was focused on just making the odometry system work and that global positioning system work. So the challenge really with dealing with that is we only get 3 encoder readings, so we don't actually get a reading of our robot's position. And the way we ended up making it work was we were able to use these 2 encoders here to figure out the angle of our robot. And after that, we were able to use trig to figure out how far we had moved in both directions by reading how far we had moved forward and how far we had moved left and right. And so that allowed us to find out an X and Y position of our robot, no matter where it was on the field. Another big thing we did this year with our code is using a simulator. So we used the Weebot simulator to physically simulate our robot before it had even been built. And this allowed us to take a CAD model and test all of our logic and all of our mathematics in our code before we ever put it on the field. So when the robot was finally fully built and we were ready to make the autonomous, test the autonomous, we had a pretty much working system and we didn't have to work out a lot of kinks.
So that's our robot game and our approach to how to solve all of its challenges that it posed. However, we would not have been able to get so far in the season without the help of our 4 amazing mentors. If you enjoyed what you saw here today and you think that you would be interested in participating in helping a team reach lofty goals such as ours, then please reach out to FTC Louisiana to become a mentor. You don't know how much it could mean to a new and upcoming team to have an engineer in the field be able to help them along the way. Once again, thank you for watching and have a great rest of your day.